next topic is from OpenLab to ASM, a set and forget approach to AI-ready data. And this is going to be by Heiko, software R&D, lab informatics system architect, and Joachim. Okay. A couple different pronunciations, so I want to make sure we get it right. Lab connectivity software product owner and project manager at Agilent. So just really quickly, Heiko is a distinguished figure in the realm of analytical lab standards, focusing on the development of data formats and communication protocols. His expertise extends to the conceptualization of lab informatics solutions, particularly for chromatography data systems and analytical data content management systems. And he has been with HP Agilent for over 2 decades, encompassing software engineering, project and program management, technical marketing management. And since 2015, his influential role is as an R&D lab informatics system architect. And Joachim holds an MS in bioengineering and a PhD in bioinformatics, both from Ghent University. He has been with Agilent since 2013. Working on technical and leadership roles. He has been product owner for a large commercial cloud-based genomics and analysis platform, and since 2025 has been working as product owner and project manager on Allotrope-related products. So with that, I will pass it over to you for your presentation. Thank you.
Right, so what is the problem we're trying to solve with the Agilent Allotrope application we're making is we want to enable AI-ready data, and for that we need this AI-ready. And so the problem is data stored in OpenLab CDS, which is the chromatography system from Agilent, is not built for AI applications. The data format is built for the CDS application, which means it's proprietary format. It's made for internal use, and it's not optimized for large-scale AI or machine learning applications. And so what are the AI requirements for data? It must be fair, as mentioned before. It must be machine readable, platform neutral, have explicit and standardized semantics, consistent structure across techniques. Let's say you have an LC dataset and a GC dataset, an MS dataset from Agilent, from Waters, from whatever vendor. You want to have the same data format so you can care about the AI application, not to care about the proprietary format and working with the data to get to the analysis. And also we want to have the data automatically generated at generation time, so we don't want to spend manual time converting proprietary data formats into a standardized data format. So as is not surprising, the ASM format or the Allotrope in general is a good concept to accomplish that. So we have chosen for the ASM approach or the ASM format, which is a simplified Allotrope format. It uses Allotrope ontologies. It's specified in JSON schemes. I have an example next slide. So these JSON schemes share commonalities between different techniques, like for the LC, the GC, LCMS, GCMS. There's like a lot of commonalities on the injection, the sample name, when it was processed, etc., etc. So all those are also shared. Now, what is specific for the LC or the GC or whatever technique is specific. And so the combination of all those building blocks makes it a very good system to work with. And basically, this ASM format eliminates the upstream proprietary or technique-specific format and gives us a standardized format to work. And so we have made, or we're making the ASM export for OpenLab application, which is an automated ETL pipeline, and it's purposely built to make life easy. So it's walk-away automation, we call it. So you set it up once, you click a button, and it will generate all your ASM files at the time of data generation. So just to give you an example of what the JSON file looks like, so there will be, Heiko has more details at the end of the presentation, but as you can see, it's like a JSON format. It's very structured, and it contains the analyst, the submitter, timestamps, volumes, and it's all in standardized units. It seems trivial, but different techniques or different vendors they use. One uses millimeters, the other one uses centimeters, the other one uses minutes, the other one uses seconds. In this ASM file, it's all standardized. All these units are predefined. So once you have your JSON file, you don't need to worry anymore about units and conversions or not. So how does this application work? So on the left-hand side, you see the lab person with files. Then they put data, the sample in the chromatography system. Then data will get produced in the chromatography data system, so the OpenLab CDS. And then it's processed. And eventually it ends up in the what we call the data storage or the content management, which is OpenLab ECM in our case. And that's where our new application hooks into. So we basically have an ASM export application that continuously monitors the ECM system. As soon as new data arrives, we'll pick it up and send it. It's called bind. So eventually the ASM file gets generated automatically and gets pushed to a customer data repository, which the customer can define remote herself. So what is the user experience for the ASM application? So it's a standalone application, which means it's not a post-processing plugin CDS. So some people might remember we had an old application or application before, which is a post-processing plugin in CDS. And then it means you need to remember to check the box where you need to click a button and then it will convert your data to an ADF file in that case. So that's not the case anymore. It's a standalone application, so you cannot forget to set it up. And it's a simple installation. It's a one-time configuration. So you define your ingestion source, which is the ECM instance, your credentials. Then you define some conversion parameters, like I want to include certain raw data, yes or no. You define your transfer destination, an Amazon bucket, local file system. You click away, you click and walk away, and once that is set up, all your data will get converted on the fly. And you have a simple web-based user interface, which I will demo in a few seconds. So maybe let's come back to the data flow. So there was a question in the last talk on legacy data, which is always a concern. So we have chosen the approach of two different data flows. So one is the automatic mode, which is what I explained. So all the data that gets produced will get picked up by the system, gets put in a queue. And on the other hand, you have the legacy or the manual mode, we call it, where you can choose, let's say I want to convert my data from 2015 or something. You can define your date range, you can define the data location that will get batch converted together with the automatic mode. So basically, all the data gets put in a big queue. So the automatic data, the automatic mode, the manual mode, big queue, then data gets converted one by one by one, and then ends up in the output location. And important to note is that it's a two-step process. So the initial phase, which you call discovery phase, means data gets detected or discovered in your data repository or your content management. It gets put in a queue, but it's not downloaded yet, so we can properly, performance-wise, manage everything. Let's say you have 100 samples that get produced at one point in time. We won't hammer your system to get all the data converted. It will be put in a queue, and then one by one we'll do the conversion and put the data in the transfer destination. So how does this work in practice? For the people familiar with the OpenLab data system, so we support multiple topologies. The one we're focused on is on the OpenLab server. For obvious reasons, we want to have big volumes of data, so we focus on the server topology. And then you have an installation. So the installation takes, installing these systems can be painful sometimes, lots of manual steps and configuring users and whatnot. So we've chosen we've put time and effort into an automated configuration system. So you do your installation of the application, which takes like 30 seconds or something. And then there's this little configuration pop-up where you define a username and a password, and then you click save, and it will interact with the existing OpenLab infrastructure, which you call the shared services. It will create permissions and privileges roles, make a connection to the database, etc. You hit save, all your configuration is done. Then you have roles which are automatically created in the OpenLab control panel. You can assign them, as you can see, ASM export. We have two ASM export admin, ASM export analyst. You can assign one of those roles to your user, and then you're set up to go. And I'm knowing that live demos always go wrong. I have some what I call an offline demo. So this is how the authentication page looks like. You see, it seems trivial to do, but it actually integrates with the existing OpenLab ecosystem. So which means if you have users already that have access to OpenLab CDS, you can reuse those users. You assign the appropriate privilege, and then they can authenticate to the ASM export application. Then we have a nice homepage, which is nothing too fancy to talk about. But then there's a configuration menu. As you can see, there's an automatic mode and a manual mode that you can configure. And there's always 3 steps to configure, which is an ingestion. So that's basically where your data sits. There's like you can configure ECM XT, which is the new ECM storage, or ECM 3.6, the legacy system. You configure your URL and then username and a password of the user that will fetch the data. And there's conversion parameters. There's not many. So raw data can be painful in JSON files, certainly for the GCMS or the 3D UV data can become very big. Like you can have like this 50 megabyte data cube blocks in your JSON files. So you can choose to exclude raw data, all the raw data, 3D UV data, 3D MS data, exclude or include. So once that is set up, you go to the transfer page or the transfer configuration. We have 2 transfer options at the moment, which is the local file system. So basically you define a path on your machine where you want to put the JSON files, or an Amazon S3 bucket. Then you hit save, and as you can see, for demo purposes, I put in incorrect credentials, so it will automatically validate whether the credentials work or not. If everything is fine, you hit save, you get a green light. If it's not fine, you get a red light. And then the final step is starting the actual discovery. Then what you need to do is select a folder or more than one folder you want to monitor on your data storage. So in this case, I chose one folder. And I have some dashboard lights at the top, which will basically validate that all the previous steps were successfully configured and tested. And then you hit start polling. So this button, bottom right, you start polling. And once that is done, all the data will get, as soon as it arrives in ECM, we'll pick up the file, convert it to a JSON file, and put it back, or put it in the configured transfer destination. So once that is done, you can close this application, you never need to look at it again. Then you have a similar setup for the manual mode. So the ingestion, conversion, transfer, you can configure it separately for both approaches, but conceptually it's the same. And then we have this queue or this discovery table, so you can define a start and a stop, a date range basically. Let's say 1st of January 25, December 31st of 25. So you'll get a long list of all the data sets. You can batch select all of those, or make some manual selections, or choose the files you want to process. You hit queue for processing, which can be thousands of data sets. You queue them, and then they end in a batch mode. They end up in the queue. And then the last step is, so after the discovery phase, there's also the processing phase, which is a process you can start and stop separately. And then once you start that, it will, as you define the number of processes, maximum of 5 at the moment, it will, in chunks of 5, process all the data that is in your queue. If there's nothing to do, it won't do anything. If the queue is full, chunk by chunk by chunk. And so you cannot, there's no risk of hammering your system. And then eventually, after waiting a few minutes, you will see these JSON files popping up on your either local disk or at Amazon. And as you can see, you make one JSON file per injection, and then you populate your data lake or the data repository with all your JSON files. And also we have an activity log, which is for compliance purposes relevant for the pharma customers. So we will track anybody that logs in the system, make changes, all the typical activity log. All right, and then that was on the current state or the coming release. So what is the future? So currently we're supporting this flow from OpenLab on the left, OpenLab CDS through ECM through JSON file. So we also plan to expand this to waters and power, which Heiko will come back onto in the next slide. And as mentioned before, we also have this legacy plugin application in OpenLab CDS for ADF exports. So we also plan to expand this standalone application to ADF files. But given the also Heiko's talk on the future of the ADF and how to go into the future, it will depend on what the future for ADF brings on how and when and what we will implement for this ADF. And then a final slide for me on the roadmap. So we plan an initial release in fall 26. So that's close after the summer. We plan to release this product. So we'll support OpenLab CDS chromatography data stored in ECM, ECM 36, so the legacy ECM, the new one. And as initial storage destination, Amazon S3 and a local file system. And support for LCGC, LCMS, and likely GCMS. We have a lot of extensions planned depending on corporate factors you're all aware of. So we plan to expand to other types of data, electrophoresis. We plan to expand to legacy systems like the ChemStation, the EasyChrome, and also including non-Agilent CDS systems, thermochrominium, waters and power, and also non-Agilent instruments that can have data in OpenLab CDS. So that was it from my side. And I think Heiko wants to add a few more details on this slide and also some JSON file examples.
So what we will support in this conversion is various techniques. So LCGC, LCMS, probably also GCMS for Agilent LCs, GCs, and single squads. There are the more detector supported, and you know from the earlier product, which was the ADF UV inverter. So we are supporting the UV detectors, VAD, MWD, VWD, fluorescence detector, the refractive index detector, the evaporative light scattering detector, and also analog to digital conversion through our UIP device. You can reach the various GC detectors, so that's basically all of what we're having available, and also the single quad mass spectrometer from Agilent. The content is what to support is the one which is mandatory, so the instrument configuration, injection sample submitter, and the process data. So from the raw data, we can put in the LC-GC chromatograms, MS, TSCs, EAC, which are stored from the OpenLab CDS, and UV spectra and mass spectrometry spectra. So we're working on the fraction collection to get this in. So the pre-implementation is already done. I can show you some examples. The only step that is missing is if a fraction spans multiple vessels, that this has to be considered in the Allotrope specification, but we're working with on this. And then the last thing is audit trail. So to get the audit trail into it, so we have already some proposal done, but we have to see how we can get this in. So this is all what's planned for this ASM export for this current solution. And let me just show you then some examples which are available today as ASMs. So I assume I need to share my screen here. Okay, so let's start with the well-known stuff. This is liquid chromatography, the usual UV part. That's a VWD. So as you know, we have the manifest, which is a liquid chromatography ASM. So you can see submitter analyst, and for each signal, we have a measurement document with the metadata like names. So we have the information, what kind of device has acquired the signal with some additional custom information like the method and the method name and the manifest version of the method. So that's some additional information that is available in custom information aggregate document. Injection information, chromatogram data cube. So we have the chromatogram data cube structure with the retention time and the absorbance units, and then the raw data here. So you can see that. And then we have the device system document. So that means the devices which are participating in the run to produce that data. And then you can already see some early version of the audit trail document about category, entity type, and all the details you would expect from an audit trail. Then we have the process data aggregate document, which explains or which lists the peak area, attention time, and whatever you have selected to be calculated by OpenLab CDS. So that is the normal liquid chromatography UV ASM. So when you have a look here at the fluorescence detector, basically the same content, but what's different here, measure is in unit RFU. So that has been standardized by Allotrope to use that. And since Agilent is acquiring the data in RIU, so we have added a conversion, which is basically a one-to-one conversion from RIU to RFU. But if customers want for luminescence unit, but if customers want to calculate back from the RFU to the original in Agilent use unit, you can have the custom information document to be able to calculate it back to luminescence unit. So for this, it's boring since it's a one-to-one comparison, but there are other scale factors where you have to use other scaling multipliers, and then you, in case you want to have the data shown as it was originally shown in the chromatography data system, you have now a means with this custom information to calculate it back to the original information. Going further, so this is refractive index units. So it's then the same structure as you have seen before. The chromatogram data cube, you will find here the refractive index units. Again, Allotrope has this standardized on RIU. So, and there is a little bit of a difference between the values which are in the process data aggregate document and in the chromatogram. So there as well, we have some calculation factors added to be able to calculate back to the values that have been originally visualized in the OpenLab CDS. Then regarding, so this is about fraction document. So you can see here a fraction collection information. So it starts with when the fraction start time, fraction end time, the volume, the trigger reason, the end trigger reason, the start volume. And so what's still missing here is the covering of the multiple vessels. So what we're also adding is here as a custom information is you can see it here. So here we have added some terms which so what's the fraction trigger reason, since these fraction trigger reasons haven't been standardized yet, so we are having specified these as an Agilent specific terminology so far, but if we are able to get this into the Allotrope, but I don't think that we can get these vendor specific terms into it. So I think that, but we have something available that lets us, that expresses how the fraction trigger reason was. Then another example here regarding GC. So these are the various GC detectors. So basically it's the same information. And then in the chromatogram data cube, we have then the various millivolts over seconds. And so again, the data, so that's also available here. And here we have a special detector, which is producing data in 25 microvolts units. So here is some example where you really need to have some calculation in case you want to visualize it with the numbers and the units that were originally visualized in OpenLab CDS. Okay, so that's the NCT, so another GC detector, but I think I want to go further with the LCMS. So this one takes a little bit here in this edit and editor, and it also shows that LCMS data is probably not just easy to be handled since the XML or the JSON is pretty long. So will be visualized in a minute. Okay. So it's just because of the size of the XML. Good. So basically, what we have here is LCMS. So with the DAD, this is a chromatogram data cube. So you know that with the absorbance units over the time. Then we have here, let me move that away, a TAC. So this is then the mass chromatogram data cube. So what you can see here in the data is so structure here. It's the counts over seconds. So that's basically a two-dimensional mass chromatogram data cube. Then we have the 3D UV. So that's a the UV spectra, which is the retention time and the wavelengths, and there's a measurement dimension, the milliabsorbance unit. So this is a three-dimensional, as you can see here, three-dimensional UV spectra data cube. And last but not least, we have here the mass spectrometry data cube. So the mass spectrum data cube, which is retention time over M% over counts, and this is in this format where each point is reflected as with these three dimensions. And this is some fast track through the various formats in live. So as I mentioned, what's just missing is the fraction collection completed and the audit trail to be able to make that nice round solution. Okay, that's all from my side. So anything, I think that's what we had. Okay. Any questions?